Well, what if I told you I had two springs that I connected together, and the first time I connected them together, I put them side by side, and then I suspended a rod from those two springs, and from that point, I hung some object with a mass of m, and I found that in doing so, the rod displaced, and now the weight hung at some lower position, so that the displacement delta x is some measurable value. And I found in the end that by putting them side by side in this manner, that spring number 1 and spring number 2 had an effective K value of 1,500 newtons per meter. And then I took those exact same two springs and I connected them end to end. In other words, I connected them in series. And then I hang a weight and do an experiment. And from experiment, I find that this time the effective K value when connected in series is 240 newtons per meter. Given that information, could you tell me what are the values of K1 and K2? So let's see if we can solve this problem together. The formula for the effective K value for springs in parallel just says add their two individual spring stiffnesses to get the effective. For springs in series, I have to take a reciprocal rule. 1 over the effective K value is equal to 1 over K1 plus 1 over K2. So let's do this. Let's use the first equation as a way to substitute into the second equation. So the first equation tells us that K2 would be K parallel minus K1. So we can make that substitution. Oh, and if we want, we could rearrange this equation in this form. K series is equal to K1 multiplied by K2 over K1 plus K2. So if I make this substitution for K2, then we can get this down to a single variable and solve just for one of the spring values. So we end up with the K value when in series is equal to K1 times the quantity K value in parallel minus K1 divided by K1 plus K parallel minus K1. So what does this give us? The K value for the series combination is equal to K1 K parallel minus K1 squared, all divided by, let's see, that's going to cancel out, so we just get K parallel. So now we have an equation that says K series multiplied by K parallel is equal to, I'll drop the 1 for now and just realize all we're doing is solving for one of the two stiffnesses. So instead of calling it K subscript 1, I'll just refer to it as K. So is equal to K times Kp minus K squared. Now let's get this in another form. This is the same thing as K squared minus Kpk plus Ks Kp is equal to 0. This is kind of like ax squared plus bx plus c is equal to 0. As long as x is the same thing as k, then I have an a value equal to 1. I have a b value equal to, what, negative kp, and I have a c value equal to the product of ks and kp. So how do we solve a quadratic like this? Don't we have k would be equal to negative b plus or minus the square root of b squared minus 4ac all divided by 2a. So we'd find the k value is equal to k parallel plus or minus the square root of k parallel squared minus 4 times k series times K parallel, all divided by 2. So let's plug in the values that were given. The K value for one of our springs would be 1500, I believe. Yeah, that's right. K parallel is 1500, K series is 240. Okay, so 1500 plus or minus the square root of 1500 squared minus 4 times 240 times 1500, all divided by 2. Well, grab your calculators. Let's see what we get. So I get 1500 plus or minus the square root of 810,000, all divided by 2. What's the square root of 810,000? Well, that's 900. So I get K is equal to 1500 plus or minus 900, all divided by 2. That's nice that this one works out to be round numbers. So K is either 2,400 divided by 2, or it's 600 divided by 2. In other words, it's either 1,200 newtons per meter, or it's 300 newtons per meter. So it turns out we've solved for both K1 and K2. Those are the two values. In fact, let's double check. K parallel should just equal K1 plus K2, so 300 plus 1,200 is indeed 1,500. That checks out. K series should equal the product divided by the sum. So this would be 300 times 1,200 divided by 1,500. And lo and behold, that comes out to 240, just like we expect. Hey, one more good question about springs in series and parallel. Goes something like this. What if I had a single spring with a length of L naught that has a K value of 500 newtons per meter? And then I get a pair of scissors and I cut right in half. So now I'm left with two springs that are half as long as the original. This one's L naught over 2, and this one's length is L naught over 2. What's the K value of either one of these half springs? Is it A, still 500 newtons per meter? After all, it's still made out of the same material. Is it B, 250 newtons per meter? Because if I cut it in half, then its K value should be half as much. Or is it 1,000 newtons per meter? Because, well, why not? Or is it D, none of the above? Well, I'll give you a chance to make your guess what you think the K value is for a spring that's been cut in half. So how many of you guessed C? Congratulations, if that was your guess, that's the right answer. One way we can argue that that's got to be the right answer, well, if I take the two springs and I put them back together, then it should be back to giving me my original K value. And to put these two half springs back together, I'd have to combine them in series with each other. Well, the formula for effective K value in series says multiply the two K values together and divide it by the sum of the two K values. So if it was still 500, if it didn't change, if you guessed the answer was A, then when you put them back together, we'd have 500 times 500 divided by 1,000. But 500 over 1,000 is 1/2, and so the effective K value wouldn't match the value it was before you cut them to begin with. No, it turns out that if they're equal to 1,000 when cut in half, there's L naught, there's L naught over 2. The K value for the spring of length L naught is 500. The K value for the spring of length L naught over 2 is 1,000. And if I were to put two of those together, a 1,000 in series with a 1,000, then the math says I should get an effective K value of 1,000 times 1,000 divided by 2,000. 1,000 divided by 2,000 gives you 1/2, and 1/2 of 1,000 is 500, and so it would be back to the original K value. So that's one way to argue that when cutting a spring in half, it becomes twice as stiff. I'll let you think up as many other arguments as you can for why the K value doubles when a spring is cut in half. And by the way, does that mean if a spring of length L0 is cut into thirds, that any one of these individual springs would have an effective K value equal to 3 times K0? I leave it up to you to decide.